close your eyes and breathe deeply with me. You're aboard a timeless vessel, cradled in velvet seats as emerald hills unfurl beyond your window. Welcome to Hafee Sleep. Tonight we surrender to the hypnotic pulse of iron and fire, the heartbeat of a steam engine. Hear the chuff, chuff, chuff like a metronome for your soul, the sigh of the boiler, the whisper of tracks beneath us. This isn't just a journey through landscapes. It's a lullaby woven from coal smoke and moonlight. Let the rhythm slow your thoughts. Your journey begins now. Imagine, if you will, the soft hiss of vapor escaping a copper vessel, the rhythmic sigh of a great iron piston, the warm glow of a coal fire reflecting on a polished brass gauge. There's something deeply calming, almost meditative, in the steady heartbeat of a steam engine. It's not just machinery, it's a living breath of human ingenuity. Today, let's unwind the story of these gentle giants together. A tale not of jarring disruption, but of warm, persistent progress that cradled the modern world into being. Our journey begins not in a soot-stained factory, but under the bright Mediterranean sun of ancient Alexandria. Around the 1st century AD, a brilliant mind named Hero crafted a wondrous little device called the Aeolipile. Picture a hollow copper sphere suspended over a pot of boiling water, with 2 curved tubes venting steam. As the vapor escaped, it caused the sphere to spin, a dancing, whirling celebration of physics. Hero saw it as a temple curiosity, a wind ball to amuse philosophers. He never imagined powering industry with it, but in that spinning sphere lay a quiet whisper of potential. Steam could move things. For centuries, it remained just that, a whisper. Fast forward, imagine for a moment, stepping back in time, not to castles or kings, but down, deep down, into the belly of 17th century England. Picture yourself descending a rough-hewn shaft, the air growing thick, damp, and chillingly cold. The only light comes from flickering tallow candles, casting long, dancing shadows on the wet rock walls. Water isn't just a nuisance here. It's a constant, dripping, seeping, flooding enemy. This is the coal mine, the vital engine fueling the early fires of industry and warming homes. But it's a place perpetually at war with the very element that surrounds it. Water. Miners, tough as the rock they hacked, face this enemy daily. Groundwater relentlessly seeped through cracks, pooled in the lowest galleries, and threatened to drown their hard-won tunnels. Every swing of the pick, every heave of the shovel, happened under the looming threat of inundation. Keeping the mines dry wasn't just about comfort. It was about survival, about keeping the coal flowing, and about protecting the enormous investments made by mine owners. Without constant pumping, the mines would simply fill up and become useless, like a ship slowly sinking. So, how did they fight this watery onslaught? The primary weapon was brute force, channeled through the patient, powerful muscles of horses. Down in the gloom, often in specially constructed underground stables or treadmills near the shaft, teams of horses walked endless, monotonous circles. Think of a giant vertical hamster wheel, but made of heavy timber. As the horses plodded forward, their movement turned a central shaft. This shaft, through a complex arrangement of gears, rods, and chains, ultimately powered a series of pumps. These pumps were marvels of leverage and simple physics for their time, often bucket chains or piston pumps housed in long wooden pipes called barrels. Imagine a series of buckets on a looped chain dipping into the sump, the lowest collection point for water, and hauling it up, spilling it out at the top into drainage channels. Or picture a simple piston. As it was pulled up inside a pipe, it created a suction that drew water up behind it, Then, as it was pushed down, it forced that water further up the pipe to the next stage. It was a laborious, multi-stage process. Water might need to be lifted in stages, perhaps 30 feet at a time, by different sets of pumps and horses before finally reaching the surface. Can you feel the inefficiency? Can you hear the rhythmic clop, clop, clop of hooves on wood? Smell the damp hay and horse sweat mingling with the earthy scent of coal? It was exhausting work for the animals, requiring frequent rotation and rest. It was incredibly expensive. Feeding and stabling large numbers of horses underground wasn't cheap. The space required for the treadmills and drive mechanisms stole valuable room from mining operations. The whole system was slow, cumbersome, and limited in how much water it could lift and how high. Mine depths and productivity were directly shackled by the limitations of equine and muscle-powered pumping. It was a constant draining battle, literally and financially. The mine owners and miners desperately needed a champion, a stronger, more tireless friend to fight the flood. Enter Thomas Savery. In 1698, this inventive military engineer, likely drawing on ideas bubbling around scientific circles concerning vacuums and steam pressure, think Denis Papin's digester, stepped forward with a solution. He patented a device he dramatically called the miner's friend, or an engine to raise water by fire. Its name alone offered hope, a friend to the beleaguered miner, powered not by hay and muscle, but by fire and water itself. What made Savery's engine revolutionary and different from the horse-powered pumps? It had no pistons, no crankshafts, no gears driven by animals. Its magic lay in harnessing two fundamental forces, the power of steam pressure and the power of a vacuum. Savery grasped a beautiful, almost poetic principle. If you could create an empty space, a vacuum, nature would rush in to fill it. And steam, that invisible force rising from boiling water, could be used to both push and pull to create that emptiness. Here's how Savery's miner's friend likely worked, step by gentle step in its intended rhythm. Imagine a sturdy copper vessel, the boiler, sitting over a firebox. Coal burns, heating the water inside. As the water boils, steam builds up under pressure inside this sealed vessel. Think of it like a giant, strong kettle building up a head of steam. Connected to this boiler are pipes leading to one or more receiver vessels, often made of copper or brass. A valve opens. The pressurized steam, eager to expand, rushes out of the boiler and fills one of these receiver vessels, pushing out any air or water that might be inside. It's like blowing up a tough balloon. The steam fills the space. Once the receiver is full of steam, the valve connecting it to the boiler is shut. Now, this sealed vessel is full of nothing but hot, pressurized vapor. Here came Savery's key trick. Cold water was then sprayed or poured onto the outside of the steam-filled receiver vessel. Think of splashing cold water on a hot glass window. It causes condensation. The cold spray rapidly cooled the metal walls of the receiver. The steam inside, suddenly chilled, condensed back into a tiny amount of liquid water. This phase change is crucial. Steam occupies a vastly larger volume than the water it condenses back into. So by turning the steam back into water, inside the sealed vessel, Savery dramatically reduced the volume of stuff inside it. This created a partial vacuum, a significant emptiness within the receiver. Now this receiver vessel was also connected via a valve at its bottom to a pipe that dipped down into the mine sump, the pool of water needing to be lifted. When another valve, a one-way check valve, at the bottom of the receiver opened, nature, abhorring the vacuum, did its thing. The The pressure of the atmosphere, pressing down on the surface of the water in the sump, which is open to the air, had nothing pushing back inside the receiver vessel except this vacuum. So the atmospheric pressure pushed the water from the sump up the pipe and into the receiver vessel, filling that emptiness. It's like putting a straw into a drink, sucking the air out to create a vacuum in the straw, and watching the liquid rush up to fill it. Except here, the sucking force was created by condensing steam, not your lungs. Savory was harnessing the entire weight of the atmosphere to do the work. This was the gentle embrace, the deep, calming breath drawing the water upwards. Once the receiver vessel was filled with water, the bottom valve to the suction pipe was closed. Then, the valve connecting the receiver to the boiler was opened again. Fresh, high-pressure steam from the boiler rushed back into the receiver vessel, now filled with water. This pressurized steam acted like a piston, pushing down on the surface of the water inside the receiver. With enough pressure built up, another valve, another one-way check valve, at the top of the receiver, leading to an outlet pipe pointing upwards, would be forced open. The pressurized steam would then push the water up and out of this discharge pipe, hopefully lifting it high enough to drain away or into the next stage of lifting. Imagine blowing forcefully into that same straw, now filled with liquid. You'd push the liquid out the top. With the water expelled, the outlet valve would close. The boiler valve might close again, and the cooling process could restart on the receiver to create another vacuum and draw up more water. Often, Savory's engines used two receiver vessels working alternately. While one was filling with steam or expelling water under pressure, the other was being cooled to create a vacuum and suck up water, aiming for a more continuous flow. It was a conceptually beautiful solution. Fire boiled water to make steam. Steam, through expansion and contraction, created a vacuum. The vacuum, aided by atmospheric pressure, lifted water. Then, steam pressure pushed the water even higher. It turned the very elements causing the problem, water and the need for fire, coal, into the solution. It promised liberation from the endless, expensive circling of horses. It was a machine powered by the elemental dance of fire and water. However, the reality, as with many first steps, was far from perfect. Savory's miner's friend, while a brilliant proof of concept, had significant limitations that prevented it from becoming the universal savior its name promised. Savory's boilers and vessels were built to withstand only very low steam pressures, perhaps only a few pounds per square inch above atmospheric pressure. The metallurgy and engineering techniques of the late 1600s weren't advanced enough to reliably contain high-pressure steam safely. Think of early kettles. They might whistle, but they weren't pressure cookers. This low-pressure limit drastically restricted the engine's power. The push phase, relying solely on this minimal steam pressure, was particularly weak. It could only lift water effectively about 20 to 30 feet, using the vacuum, suck, and maybe another 20-30 feet using the steam, push, but with rapidly diminishing efficiency. Lifting water hundreds of feet from deep mines required multiple engines working in stages, which was complex and costly. More terrifyingly, these low-pressure boilers were still prone to catastrophic failure. Welds could burst, seams could split. A boiler explosion, even at low pressure, in the confined, flammable environment of a mine was a devastating disaster, scattering deadly shrapnel and scalding steam. The friend could become a deadly foe. This inherent danger made mine owners understandably cautious. While theoretically using fire more efficiently than feeding horses, the early Savory engines were incredibly inefficient in practice. Creating the vacuum required constant reheating and cooling of the receiver vessels. Spraying cold water onto the hot metal wasted enormous amounts of thermal energy. It was like constantly heating a pot only to immediately dump cold water into it. They consumed vast quantities of coal relative to the amount of water they lifted, especially compared to what would come later. This high fuel cost ate into the potential savings on horse maintenance. Operating the valves required manual labor or complex, unreliable clockwork mechanisms. The constant thermal cycling, heating, and cooling put immense stress on the metal, leading to leaks and frequent breakdowns. The engine could only work intermittently, not with the smooth, continuous flow needed for large-scale dewatering. Getting a good seal on the valves and joints with the materials available was also a constant challenge. So, was Savory's engine a failure? Absolutely not. It was a vital, groundbreaking North Star plow. It was the first practical device designed to harness steam power for mechanical work, pumping water. It proved, beyond philosophical curiosity like Hero's Eolipoli, that fire and water could work in harmony to ease human labor. It demonstrated the power of the vacuum and steam pressure in a real-world application. It provided a tangible answer to a desperate need, even if the answer wasn't perfect. Mine owners did install Savory engines, particularly in shallower mines or situations where the risk and inefficiency were deemed acceptable compared to the cost of endless horses. It sparked imaginations. Savory's patent, notably, was broad enough to cover any engine raising water by fire, which later became significant. His work laid the essential groundwork, highlighting both the immense potential and the critical challenges. It set the stage for the next generation of inventors, like Thomas Newcomen, who would witness Savory's principles, understand its limitations, and think, how can we make this stronger, safer, more efficient? How can we harness that atmospheric push more directly? The miner's friend was the fragile, pioneering first breath in the long, rhythmic life of the steam engine, born in the dripping darkness but pointing the way towards a future powered by steam's persistent, transformative sigh. It was the moment humanity first began to truly listen to the power whispering in the kettle's song. Enter Thomas Newcomen. He wasn't some aristocratic scholar tucked away in a university. He was a blacksmith and ironmonger, a practical man from Dartmouth in Devon, whose hands were calloused from shaping metal, whose eyes were sharp from solving tangible problems. He understood materials, forces, and mechanisms from the ground up. Think of him standing in his workshop, surrounded by the clang of hammers and the smell of hot iron, pondering the desperate pleas from the mines. He knew about Thomas Savory's earlier miner's friend, a device that used steam to create a vacuum and suck water upwards. But Savory's engine had serious flaws. It relied directly on steam pressure and vacuum, making its boilers prone to terrifying explosions, a very real danger with the metallurgy of the time. More crucially, it could only lift water about 30 feet, useless for the deeper mines becoming common. It was a step, but not the giant leap needed. Newcomen watched, thought, and tinkered. He had patient hands indeed, carefully crafting parts, testing ideas, learning from failures. He possessed that watchful eye of the true craftsman, observing how steam behaved, how condensation worked, how the very air around us has weight and force. Around 1712, all that patient work culminated in something revolutionary. High up on the windswept, misty hills of Staffordshire, at the Connigree Coal Works near Dudley Castle, Newcomen, likely working with his assistant John Calley, and perhaps inspired by earlier ideas from others like Denis Papin, unveiled his atmospheric engine. Forget sleek efficiency. This was a beast, a testament to brute strength harnessed by clever design. The heart of its operation was fundamentally different from Savory's. Instead of relying on potentially explosive steam pressure to push water up, Newcomen harnessed the immense, silent power of the atmosphere itself to pull a piston down. This is the key to understanding its slow, dignified rhythm. Let's build a mental picture, piece by piece. Imagine a massive wooden beam. Think of the trunk of a mighty oak, pivoted right at its center like a colossal seesaw. This beam, called the Great Working Beam, or simply the beam, was the engine's backbone, translating force across its length. Now, dangling from one end of this beam was a heavy iron chain. At the bottom of that chain, inside a stout vertical cylinder, hung a solid iron piston. This piston wasn't sealed perfectly, like in later engines. It was more like a large, heavy disc fitting loosely inside the cylinder. Above it sat a hefty rod connected back to the beam. Here's where the magic, or rather the physics, began. Down below, a coal fire glowed merrily in a furnace, heating a large, closed boiler filled with water. Steam, gentle as a sigh escaping tired lungs, was piped from this boiler into the space underneath the piston inside that vertical cylinder. Filling the cylinder, the steam pushed the piston all the way up to the top. Think of it like inflating a balloon under a plate. The plate lifts smoothly. This was the quiet, preparatory phase. Then came the crucial moment. A valve opened, spraying a jet of cold water directly into the cylinder filled with steam. What happened? The cold water instantly condensed that hot steam back into water. Steam takes up vastly more space than water, so when it condenses, it effectively disappears, leaving behind nothing. Or more accurately, a partial vacuum, a space with very little air pressure inside the cylinder. Suddenly, the immense weight of the Earth's atmosphere, that ocean of air miles deep pressing down on everything, had nothing pushing back against it inside the cylinder above the piston. Picture a giant invisible hand pressing down on the piston from above. With a distinct, muffled thump, a sound miners likely came to love, the atmospheric pressure slammed the heavy piston down to the bottom of the cylinder. Remember that massive wooden beam? The chain holding the piston was attached to one end. So, when the piston was forced down by the atmosphere, it pulled that end of the beam down. Because the beam was balanced like a seesaw, when one end went down, the other end had to go up. Attached to this other end was another chain or rod, which connected deep down into the mine shaft to the actual pump mechanism, usually a set of buckets or plungers designed to lift water. So, as the beam's far end rose, it lifted the pump rods, drawing water up from the depths. It was a beautiful, direct transfer of force. The atmosphere pushes the piston down, the piston pulls the beam down, the beam lifts the pump up, water rises. Now, the piston is down, the water has been lifted one stroke. What next? The cycle needed to repeat. Valves closed off the cold water spray and opened the steam inlet again. Steam rushed back into the cylinder beneath the piston, filling the vacuum. Since the piston was loose-fitting, the steam could easily flow around it. This steam pressure wasn't strong enough to lift the piston against the weight of the pump rods and the water on the other end of the beam. Instead, it simply equalized the pressure above and below the piston, neutralizing the vacuum's pull. Here's where gravity took over. The pump rods and water column deep in the mine were incredibly heavy. This weight, hanging on the far end of the beam, which was currently up, naturally wanted to fall back down. As it descended, it pulled its end of the beam down, which consequently lifted the piston end, and the piston itself, back up to the top of the cylinder, ready for the next injection of steam and cold water. The slow, dignified rhythm came from this alternating dance. The powerful atmospheric-powered downstroke doing the hard work of lifting water, followed by the slower gravity-powered return stroke resetting the piston. Chug, pause. Whoosh, chug, pause. Whoosh. It was a lullaby of leverage, gravity and atmospheric pressure working in a simple, powerful, and surprisingly reliable, gentle duet. This reliability was Newcomen's triumph. Yes, his engine was incredibly inefficient by modern standards. It guzzled coal because the entire cylinder was cooled down with every cold water injection. The next blast of steam had to waste vast amounts of energy just reheating the cold iron walls before it could even start pushing the piston up for the reset, a problem James Watt would later brilliantly solve. They were enormous, expensive to build and install, and required constant attention from an engine man to tend the fire and operate the valves, often via a simple system of strings and plugs called the plug rod that automated some valve timing based on the beam's position. But crucially, they worked. They were robust, built with the heavy iron and timber craftsmanship Newcomen understood. They didn't rely on high-pressure steam, making them significantly safer than attempts like Savory's. And most importantly, they could lift water from depths far exceeding 30 feet, hundreds of feet in fact, making deep mining viable. The impact was immediate and profound. Word spread rapidly through the mining communities. By 1775, just over 60 years after that first engine in Staffordshire, over 100 Newcomen engines were chugging away across Britain and Europe. Their steady chug-chug became the heartbeat of the coal fields, the tin mines, and later, even early waterworks. For the miners, the psychological relief was immense. These weren't just machines. They were iron guardians. Knowing that a Newcomen engine was tirelessly pumping overhead meant the terrifying specter of sudden, deadly flooding receded. It meant mines could operate deeper and longer, securing jobs and boosting the vital coal supply. Miners could indeed sleep easier, not just physically safer, but with less anxiety about the mine's survival. The rhythmic thump and sigh of the engine became a sound of security, of progress, of coal being won from the depths to fuel the burgeoning industrial revolution that was just beginning to stir. That patient blacksmith, whose atmospheric engine, with its slow, dignified thump-chug, became the iron guardian of the mines? Well, hold on to your hat, because the story of steam is about to take a brilliant, efficiency-obsessed turn. While Newcomen's engines were reliable workhorses, they had a gluttonous appetite. They devoured coal, and it was this very inefficiency that caught the eye and then the brilliant mind of a young Scotsman named James Watt. If Newcomen built the sturdy bridge into the age of steam power, Watt refined it into a sleek, powerful highway. Picture Glasgow in the mid-1760s. The clatter of industry is growing, and Newcomen engines are chugging away, but their limitations are becoming painfully clear, especially to a sharp-eyed instrument maker at the University of Glasgow. James Watt wasn't just a tinkerer, he was a scientist of mechanics, deeply curious about the why behind the how. His workshop wasn't just cluttered, it was a sanctuary of inquiry, filled with delicate scales, finely crafted telescopes, and models of machines, including a small-scale model of a Newcomen engine that needed fixing. It was while wrestling with this little model, trying to understand why it performed so poorly despite faithfully copying the big engines, that Watt had his earth-shattering, coal-saving revelation. The fundamental problem with the Newcomen engine Watt realized, wasn't laziness or poor construction. It was baked right into its very cycle. Remember that crucial moment in the Newcomen engine? The jet of cold water spraying into the cylinder to condense the steam and create the vacuum? That was the heart of the waste. Think about it like this. Imagine you have a heavy cast iron teapot. You spend time and fuel getting it piping hot to brew your tea. But then, just as it reaches the perfect temperature, you dump a bucket of cold water over it. The teapot instantly chills. Now, if you want more tea, you have to start all over again, burning more fuel to reheat that cold, heavy iron teapot from scratch before you can even begin heating the water inside. That's essentially what was happening inside the Newcomen cylinder with every single stroke. The cylinder was the teapot. It was a massive piece of iron. To create the vacuum, cold water was sprayed directly inside it, chilling the cylinder walls dramatically. Then, for the next stroke, live steam from the boiler was injected into this cold cylinder. What happened? A huge portion of that precious, fuel-generated steam instantly condensed back into water the moment it touched the cold iron walls. It wasn't pushing the piston up, it was just sacrificially reheating the cylinder, drop by drop, until the metal was warm enough for the remaining steam to actually fill the space and push the piston. Only then could the cycle continue. It was a constant, energy-sapping battle. Heat the cylinder, then deliberately cool it, then waste steam reheating it. Watt saw this alternate heating and cooling as nothing short of staggering waste. It was like constantly reheating your teapot, only to immediately douse it in cold water again. Enormous amounts of coal were burned not to do useful work, but just to overcome this thermal seesaw inside the cylinder itself. This is where Watt's genius ignited. Strolling near Glasgow Green on a Sunday afternoon in 1765, the solution flashed into his mind with startling clarity. Separate the processes. Why must condensation happen inside the main cylinder? What if the cylinder could stay perpetually hot while the steam was condensed somewhere else? His revolutionary idea was the separate condenser. Imagine the main cylinder, home to the piston. Watt envisioned keeping this cylinder always hot, ideally as hot as the steam entering it. No more chilling it with cold water. Instead, he added a separate closed vessel, the condenser, connected to the cylinder by a valve. When it was time to create the vacuum, after the steam had pushed the piston up, Watt would close the steam inlet valve to the cylinder and open a valve connecting the cylinder to this separate condenser. The condenser itself would be kept cold, perhaps by being immersed in a cold water bath. Here's the beautiful physics. The steam inside the cylinder, seeking equilibrium, would rush into the cold condenser. There, it would instantly meet the chilled surfaces and condense rapidly back into water, creating a powerful vacuum within the condenser and the pipe connecting it to the cylinder. Crucially, because the condensation happened away from the main cylinder, the cylinder walls stayed blissfully hot. The vacuum now pulled on the piston just as effectively as in the Newcomen engine, sucking it down for the power stroke. But the magic was in the aftermath. When it was time for the next intake stroke, Watt simply opened the steam inlet valve again. Live steam rushed into the still hot cylinder. Because the cylinder wasn't cold, very little steam wasted itself reheating the metal. Almost all of it expanded immediately, pushing the piston up powerfully and efficiently. The cylinder could exhale its spent breath, the steam destined for condensation, into the separate condenser, keeping its own heart, the cylinder, cozy and efficient. The impact was breathtaking. By eliminating this constant, massive heat loss in the cylinder, Watt's separate condenser alone slashed coal consumption by a staggering 75% compared to a comparable Newcomen engine. It wasn't just an improvement, it was a transformation. Suddenly, steam power became dramatically more economical, not just for pumping mines, but for a whole new world of applications. It was like replacing a gas-guzzling truck with a fuel-efficient car. The same job could be done for a fraction of the cost. But Watt, the meticulous perfectionist, wasn't finished tuning his instrument. He saw other leaks in the Newcomen design, leaks of power, not just heat. In the atmospheric engine, the cylinder was open at the top. Steam filled the cylinder below the piston, pushing it up, but the space above the piston was just open to the air. This meant the power stroke was only on the downstroke, driven by atmospheric pressure after condensation created the vacuum. The upstroke was passive, relying on gravity pulling down the heavy pump rods on the other end of the beam to reset the piston. Watt thought, why not harness steam power for both strokes? He sealed the top of the cylinder completely. Now, he could control the steam on both sides of the piston. He added steam-tight packing, improved seals, like stuffing boxes with hemp or leather, around the piston rod where it exited the cylinder top, to prevent steam from leaking out. This paved the way for his next masterstroke, the double-acting engine. Imagine the piston sealed inside its cylinder. Watt arranged a system of valves, later perfected into his elegant slide valve. For the downstroke, steam enters the cylinder above the piston, pushing it down. Simultaneously, the space below the piston is connected to the condenser, creating a vacuum there, which further pulls the piston down. This combined push-pull made the downstroke incredibly powerful. Then, for the upstroke, steam is directed below the piston, pushing it up. Simultaneously, the space above the piston is connected to the condenser, creating a vacuum above it, which pulls the piston up. Now both strokes were powered by steam. It was like giving the engine a steady inhale and exhale of pure power, doubling the work output for the same cylinder size compared to the single-acting Newcomen style. The rhythm became smoother, more powerful, and even more efficient. Finally, Watt turned his attention to control. Early steam engines, including his first models, could be temperamental. Their speed varied wildly depending on the load or the boiler pressure. For applications like driving factory machinery, where looms or spinning frames needed constant, reliable speed, this was a problem. Enter Watt's partner, the visionary industrialist Matthew Boulton of the Soho manufactory near Birmingham. Boulton understood the needs of factories and pushed Watt for solutions. Watt's answer was both simple and ingenious: the centrifugal governor. Picture this: two heavy brass balls, each attached to a vertical spindle via hinged arms. As the spindle rotates, driven by the engine's output shaft, centrifugal force flings the balls outwards. The faster the engine runs, the higher the balls fly. As they rise, they pull down on a sleeve connected to a lever. This lever is linked to the steam throttle valve. If the engine speeds up too much, the balls fly higher, pulling the sleeve down, which partially closes the steam inlet valve, reducing steam flow and slowing the engine down. If the engine slows too much, the balls drop lower, the sleeve rises, opening the steam valve wider, allowing more steam in and speeding the engine up. It was pure automatic feedback control. Those spinning brass balls acted as the engine's own heartbeat regulator, constantly sensing the speed and gently adjusting the steam flow to maintain a steady, rhythmic pace, no matter the load. It was the birth of automation in power systems. So, James Watt wasn't just an inventor. He was the master orchestrator of steam. He took the robust, coal-hungry rhythm of Newcomen's atmospheric engine and transformed it. With his separate condenser, he gave it stunning efficiency. By sealing the cylinder and making it double-acting, he unleashed its true power on both strokes, and with the centrifugal governor, he bestowed upon it a graceful, self-regulating constancy. He didn't just make steam engines cheaper to run. He made them powerful, reliable, and controllable enough to become the beating heart of the factories, forges, and mills that would define the Industrial Revolution. He truly was the maestro, meticulously tuning the raw power of steam into an instrument capable of driving the modern world. His workshop contemplations, born from observing a model engine's flaws, resonated into an efficiency revolution that echoed across continents. Watt's refinements transformed steam power from a mine's workhorse to industry's quiet companion. Soon, these engines hummed inside factories, their rotary motion turning the wheels of cotton mills and iron foundries. No longer bound to rushing rivers, mills could nestle anywhere, even in bustling towns. The rhythm of looms and lathes now synced to steam's pulse, steady as a metronome. Workers might not have noticed the change at first, but their world grew warmer, drier, and oddly more serene. The clatter of water wheels gave way to the softer thrum of pistons, a sound as comforting as a hearth in winter. That steady thump, thump, thump was the heartbeat of industry, making cloth, forging iron, powering progress. But steam, it turned out, had an even grander dream. It wasn't content to stay indoors. It yearned to stretch its legs, to feel the wind, to bridge distances. And in doing so, it didn't just move goods. It transformed how we experience the very world around us, shrinking continents and smoothing journeys with a power that felt, strangely enough, both mighty and profoundly calming. So, let's step outside that factory door, breathe the open air, and witness the moment steam truly learned to walk, or rather, to roll. Picture Wales, 1804. The air is damp, smelling of wet earth and coal smoke. Rain slicks down onto newly laid iron rails at the Penydarren Ironworks. Standing on those rails is something entirely new. Richard Trevithick's locomotive. It wasn't sleek. It was a compact, muscular beast of iron and fire. Think of a giant inverted copper kettle on wheels, with a chimney belching smoke and a piston rod chuffing furiously. Trevithick, a brilliant, restless Cornishman, was a gambler with steam, while Watt, cautious and protective of his patents, had largely stuck with low-pressure engines for safety. Trevithick boldly embraced high-pressure steam, so this was the key difference. Remember Watt's engine? It used steam pressure and vacuum. The atmospheric pressure did much of the heavy work on the downstroke after condensation created a vacuum. Trevithick tossed out the vacuum. He thought, why rely on the absence of pressure when steam itself, squeezed tighter, could be so much stronger? His boilers, built stronger with better iron and clever engineering, contained steam at pressures Watt would have blanched at, perhaps 5, even 10 times higher. This high-pressure steam wasn't just gently pushing a piston, it was expanding with explosive force, driving the piston with a direct, powerful shove. Steam's gentle push became a confident stride, this pure expansion. Principle, letting the steam do all the work by pushing outwards as it expanded, was the breakthrough needed for mobile power. A vacuum engine needed a constant supply of condensing water and a big, heavy condenser. Trevithick's high-pressure engine was simpler, lighter, and crucially, self-contained. On that rainy February day, this compact powerhouse proved its mettle. With a hiss and clatter that must have been startling, it hauled an astonishing load, 10 tons of iron bar and 70 men clinging to wagons behind it. Think about that for a second. 70 wide-eyed, probably slightly nervous, pioneers of rail travel. The noise would have been significant. The chuffing exhaust, the clank of rods, the rumble of iron wheels on iron rails. But beneath that mechanical symphony, Trevithick and those aboard grasped something profound, a deep, underlying calm born of unprecedented strength and certainty. Horses, magnificent as they were, strained and sweated, needing rest and fodder. This iron horse just kept going, fueled by coal and water, tireless. Horses couldn't match this strength. It was a glimpse of the future, raw, untamed power unleashed on rails. Trevithick was a visionary, but he was also unlucky, and perhaps too far ahead of his time. His early locomotives were heavy, broke rails not designed for such loads, and his business ventures often faltered. The world wasn't quite ready, but the seed was planted. Other engineers, particularly in the coal mines of northern England, saw the potential. Locomotives like George Stephenson's early Blucher began shunting coal wagons more efficiently than horses ever could. But the real leap forward, the machine that truly announced the railway age, arrived at the Rainhill Trials in 1829. This was a competition, a public spectacle designed to find the best locomotive for the revolutionary New Liverpool and Manchester Railway, the world's first intercity line designed from the start for steam power. Enter George Stephenson's rocket. Compared to Trevithick's chunky Pioneer, the rocket looked almost dainty yet purposeful. But its real genius was hidden inside. Stephenson and his son Robert, along with the brilliant Henry Booth, incorporated several key innovations. Most revolutionary was the boiler. Instead of a single flue pipe running through a large boiler of water, like Trevithick's, the rocket's boiler was studded with 25 small copper tubes. Picture it, a horizontal cylinder packed tightly with these tubes, like warm capillaries running through its core. Fire burned fiercely in a firebox at one end. The hot gases didn't just go straight out the chimney. They were forced through all these small tubes, completely surrounded by water, before escaping. This massively increased the surface area, where heat could be transferred from the fire to the water. Water turned to steam much faster, generating far more high-pressure steam, far more efficiently. It was like giving the boiler 1,000 tiny mouths breathing fire into the water, turning it into a roaring powerhouse of vapor. The rocket also featured a blast pipe. Stephenson realized that simply exhausting the spent steam up the chimney wasn't enough. By narrowing the exhaust pipe, he created a powerful blast of steam shooting upwards. This blast actually sucked the hot gases from the firebox through the boiler tubes with much greater force, making the fire burn hotter and brighter. A self-reinforcing cycle of power. It was a masterstroke of efficiency and power generation packed into a relatively light, swift machine. At Rainhill, the rocket dazzled. It didn't just win. It left the competition in the dust. It reached speeds previously unimaginable, nearly 30 miles per hour, reliably hauling loads. It proved steam locomotion wasn't just possible. It was practical, powerful, and fast. Suddenly, the potential exploded. Trains weren't just for hauling coal from pitheads anymore. The Liverpool and Manchester Railway opened in 1830, and the world watched in awe as steam locomotives began carrying people. This is where the true magic unfolded, the profound shift hinted at by that profound calm. Imagine being a traveler before the railway. A journey from, say, London to Manchester meant days crammed into a bone-rattling stagecoach, lurching and jolting over muddy, rutted roads. It was expensive, uncomfortable, slow, and often dangerous, prone to breakdowns, bandits, and accidents. Now, step into a railway carriage. Yes, the early ones were basic, perhaps open to the weather or smoky, but they ran on smooth iron rails. The ride, while perhaps bumpy by today's standards, was a revelation. Gone was the violent jolting. Instead, there was a gentle, rhythmic sway, the steady clickety-clack of wheels passing over rail joints, and above it all, the reassuring, rhythmic chuff, chuff, chuff of the locomotive up ahead, echoing through valleys, especially haunting and beautiful at dusk. It was a constant, predictable sound, a lullaby of progress. The effect on people's lives was revolutionary. The world shrank. Journeys that took days now took hours. A farmer could load his fresh milk onto a morning train and have it sold in a city market that same day. Impossible before. A clerk in a soot-stained industrial city could, for the first time, dream of a weekend escape. Pack a bag on Friday evening, board a train, and wake up Saturday morning by the sea, breathing fresh air at a newly accessible seaside resort. Families separated by distance could visit far more often. Letters, carrying news, love, or business deals, sped across the country in hours instead of weeks. Ideas, culture, and people began to flow together like never before. It fostered a sense of connection, of a nation, and eventually a world drawing closer. This new speed even forced us to reconsider time itself. Before railways, time was local. London time was a few minutes different from Bristol time, and it didn't really matter. But when trains started running complex schedules across vast distances, this local variation became chaotic and dangerous. How could you publish a reliable timetable if every town set its clocks differently? The solution? Standardized time zones. The railways effectively synchronized the nation, and later the globe, to the same gentle tick. They imposed a new, shared rhythm on society, a rhythm defined by the precision and predictability that steam rail travel demanded. It was the world learning to march, quite literally, to the beat of the steam engine's drum. Now, let's turn our gaze to the water. While iron horses were conquering the land, steam was also learning to tame the waves, and in a way that felt, surprisingly, even softer than its land-based cousin. The challenge of moving a ship by steam was immense. Water is far denser than air, requiring enormous power. Early attempts were often clumsy paddle wheels mounted on the sides, driven by low-pressure engines similar to Watt's beam engines. They were slow, inefficient, and vulnerable in rough seas. The pivotal moment arrived in 1807 on the majestic Hudson River in New York. Robert Fulton, an American inventor with a knack for practical application, though he certainly built upon the work of others like John Fitch and William Symington, launched the Chappeur-Tourteau, North River steamboat, soon famously known as the Warrior. Clermont. Powered by a Boulton-Watt-style low-pressure steam engine driving two large side-mounted paddle wheels, it wasn't fast, maybe 5 miles per hour, but it worked. It worked reliably. Fulton didn't invent the steamboat, but he made it commercially viable. Picture the scene aboard the Clermont on its maiden voyage from New York City to Albany. Passengers, perhaps initially skeptical, standing on deck. The engine starts. A deep, rhythmic thumping below decks. The paddle wheels begin to churn the water, not with the frantic splashing of oars, but with a powerful, deliberate, almost graceful rotation. The banks of the Hudson, instead of sliding past erratically as they would under sail, sometimes fast with a fair wind, sometimes agonizingly slow or even backwards when tacking against the wind, now began to glide past, steadily, relentlessly, predictably. Passengers could sip their tea without fear of sudden lurches as sails caught the wind or the ship tacked. They could read, converse, or simply watch the scenery unfold with a new sense of ease and certainty. Steam-powered ships didn't battle winds. They moved with serene certainty. The wind might howl, the current might run strong, but the deep thump, thump, thump below decks, the steady churn of the paddles, promised forward motion. The captain was no longer at the mercy of the elements in the same way. He had a measure of control. A mechanical will be driving the vessel onwards regardless of the capricious breeze. This serene certainty was steam's greatest gift to maritime travel. The impact on rivers and coastal waters was immediate and transformative. Steamboats became the vital arteries of continents. In America, they opened up the vast Mississippi and Ohio river systems, carrying settlers west, bringing goods east, knitting a young nation together. In Europe, they connected ports, islands, and navigable rivers with unprecedented reliability. But the ambition grew bigger, crossing oceans. The first transatlantic crossings by steam-assisted ships, often hybrids with sails still vital, were tentative, long, and fuel-hungry. But the vision was clear. Engineers like Isambard Kingdom Brunel pushed the boundaries with leviathans like the SS Great Western and later the revolutionary SS Great Britain, the first iron-hulled, screw-propeller-driven ocean liner. The key evolution was moving from paddle wheels, vulnerable in storms, inefficient, to the submerged screw propeller, especially once powered by more efficient compound steam engines that use steam expansively in multiple cylinders. This made ocean-going steamships truly viable. Think about what this meant for global connection. Before reliable steam, crossing the Atlantic was a weeks-long gamble on the winds and weather. Sailing ships could be becalmed for days or battered by storms. Arrival dates wildly uncertain. Trade routes were dictated by seasons and prevailing winds. The trade wind routes weren't just a name, they were a necessity. Spices from the East Indies, silks from China, tea from India, cotton from America. Their arrival was seasonal, often delayed, always uncertain. Steam changed all that. Trade routes gentled. Steamships could depart and arrive on schedules. They could take more direct routes, less beholden to prevailing winds. The monsoons in the Indian Ocean became less of a barrier. Cargoes began arriving like clockwork. This reliability revolutionized global commerce. It meant factories could plan production based on predictable raw material deliveries. Markets could be supplied consistently. The price and availability of goods became more stable. The world's economies began to synchronize, linked by the regular pulse of steamship lines. For passengers, the ocean transformed. While early steamship travel was still arduous and expensive, it offered a predictability sailing ships couldn't match. The journey time steadily decreased. Comfort increased, especially on purpose-built liners offering cabins, dining saloons, and even a touch of luxury. The ocean, once a fearsome frontier, now felt a little more like home. The constant thrum of the engines, the vibration of the deck, the sight of the unwavering plume of smoke from the funnel, these became familiar, reassuring signs of progress, of human mastery over the vastness. Letters could be sent with reasonable expectation of arrival. Emigrants could embark with a clearer idea of when they'd reach their new life. Families separated by oceans could maintain connections in ways unimaginable just decades before. The terrifying, awe-inspiring expanse of the sea became a traversable highway. The steamship didn't eliminate the ocean's power or danger, but it tamed its unpredictability, instilling a new sense of confidence and connection. So, whether it was the rhythmic chuff-chuff echoing down a green valley as a train snaked its way towards the coast, or the deep, resonant thump-thump-thump, vibrating through the deck of a steamship steadily pushing through the Atlantic swell, steam power reshaped our experience of distance and movement. It replaced the jarring, uncertain, and often arduous journeys of the past with something new. A sense of reliable progress, of scheduled arrival, of the world becoming tangibly smaller and more accessible. It brought fresh milk to city tables, seaside breezes to factory workers, and spices to distant lands with reassuring regularity. It synchronized our clocks and connected our hearts across continents. The profound calm wasn't the absence of noise. The early trains and ships were certainly noisy, but the profound absence of doubt. It was the calm that comes from knowing the engine would keep going, the wheels would keep turning, the paddles or propeller would keep churning, and you would get where you were going, on time. It was the sound of the world knitting itself together, one confident, steam-powered stride, one serene, paddle-churned mile at a time. The iron horse and the iron ship became more than machines. They became the carriers of a new era, defined not just by speed, but by the deeply soothing certainty that steam power brought to human journeys. Steam's legacy is etched in the gentlest parts of our lives. It ended the whip-crack urgency of horse travel, replacing it with the scheduled peace of a train timetable. It turned factories from drafty, water-splashed mills into places of predictable warmth, and it birthed communities, railway suburbs where commuters could work in smoky cities but return to gardens and birdsong. Yes, steam eventually yielded to diesel and electricity, its efficiency a modest 5 to 7% compared to diesel's 30-40%. But its spirit endures. Heritage railways still run today, where families ride behind a puffing locomotive, lulled by its rhythm. Preservationists, like those at the Strasbourg Railroad, tend to these iron elders with reverence, their workshops echoing with the soft taps of hammers on boilers. A living lullaby of care 285. So, the next time you hear a tea kettle whistle, think of Hero's spinning sphere, Newcomen's sighing piston, Watt's warm cylinder, and Trevithick's chuffing locomotive. They weren't just machines. They were companions in our journey toward a calmer, more connected world. Steam didn't force progress. It breathed life into it, one warm, soothing stroke at a time. And in that gentle persistence, the quiet triumph of water turned to motion, we find a timeless comfort, the reassurance that even the mightiest changes can unfold with grace. As the fire dies down and the last embers fade, the steam engine story lingers like warmth in a stone hearth. It reminds us that progress, at its best, isn't a roar. It's a steady, reliable hum in the background of our lives, a testament to the quiet power of patience and pressure. And in that thought, there's a deep, abiding peace. And just like that, our iron guardian sighs into the twilight. The pistons slow, the steam settles, and the world softens into quiet. Remember, friends, progress wasn't forged in noise alone, but in the rhythm between breaths, in the steady chuff of an engine, the deep thrum of a ship, the heartbeat that lulled an age toward calm. Tonight, let your mind drift like steam over still water. Let the weight of centuries, of coal dust and courage, of pistons and patience, lift from your shoulders. Close your eyes, and let history's gentle hum carry you deeper. This is Hafee Sleep, where the past cradles your present. Rest deeply. Good night.